Hey, so in section 2.5, we're going to be talking about continuity. So we know what it means for something to be continuous, but let's go ahead and look at this graph and see where it's discontinuous and see how we can use what we've learned about limits to make this definition of continuity a little bit more defined using calculus terms. So if we look at this function here, let's just go ahead and highlight where it is discontinuous. So if I were to be drawing this with a pencil, I would start here, and I would have continuity until I hit about this point, and this point, and here as well, and then I would end on this point. So what we have is that our function is going to be discontinuous when x equals 2, 4, and 6. And we're also going to be looking at the endpoints too. So let's go ahead and write those down. So the endpoints are going to be when x equals 0 and 8. Now, if we look at these different points and talk about their limit structures, which is what chapter 2 is all about, what we can see here is the limit of this function as x approaches 2 does not exist. Okay, so that would make us definitely fail having continuity since the left hand and the right hand sides don't match up. Now, when x approaches 4, of our function f of x, well, the limit does exist. So if we look back up, what we can see is as we approach 4 from the left or the right side, it looks like our function is approaching 7. So even though the limit exists here, why is it still not actually continuous? Well, the reason is that that doesn't actually equal the function value at 4. What happens is if you actually plug in 4 into our function, what we're going to get out, f of 4, is we're going to get out the point 8. Now, the issue at 6 is all over the place, so one issue at 6 is as we approach 6, our function does not have a limit that exists, okay, because they go to infinity. Another issue here is if I actually tried to plug 6 in, it would also not exist. So for a function to be continuous, what we have to do is that we have to meet these 3 conditions. So the first condition is that as we approach a value a, we really want that limit to exist. Okay? So as we approach a, it would be really cool if both sides of the function approach the same place L. Okay, so our limit. The other thing is that if we plug a into our function, we want it to be defined. So what that means is if I plug a into my function, it would be really cool if I actually got f of a out. Now, the last thing we want for a function to be continuous is that we want f of a to line up with the limit. So for example, if we look at this point here, the limit exists, okay, it equals 7. Our function value exists, it equals 8, but since they're not in the same spot, it's still not continuous. So the very last thing we need is that we need the limit as x approaches a to equal our function value. If all 3 of those things happen, then what we have is that we have a continuous function at that point a. Now, if we fail some of these conditions, they have special names. So let's go back up to our example. Here, what this is called a jump discontinuity. So if the limit from the left-hand side doesn't match the limit from the right-hand side, it's a jump discontinuity. You can kind of think if there is a guy running from left to right on our function, he would have to jump to get from one side to the other. This here, it looks like it would be continuous, but we just have to fill in that spot that's empty. This is called a removable discontinuity. And last but not least, here where we have this asymptote, okay, and we have one side of our function going to negative infinity and the other side going to positive infinity, this is called an infinite discontinuity. So those are the three different discontinuities we're looking at. And as well, here are the three conditions that have to be met for a function to be continuous at a point. Now, just because a function isn't continuous at a point, okay, doesn't mean we still can't talk about what kind of continuity it does have. So, there is something called left continuity. What that is that as we approach a function from the left, our limit equals our function value. So, as an example, okay, if I'm approaching from the left-hand side, that means that I would have a filled in hole here, okay? And then maybe I have an open hole over here. This would be a left continuous function. Now, a right continuous function would be the other way around. So let's say I'm approaching it from the left, but my function isn't actually defined there, but it is as I approach from the right. Okay? So when we start to talk about functions and whether they're continuous, we want to be definitive. Are they overall continuous? Are they left continuous or right continuous? So again, if we look back up at this example, this interval here would be left or right continuous. Well, we don't have a filled in spot on this little piece as we approach from the left-hand side, but we do, so this would be right continuous. As well, this piece here would also be right continuous. Okay? And then these other pieces that we have would be neither. So we'll look at some examples of that a little bit later. All right, now that we have a couple of definitions under our belt, let's go ahead and try some examples. So let's determine the intervals for which this function is continuous and determine if they are left, right, or neither continuous. So, first off, we're given the definition of this piecewise function, and we're also given a graph. So what I'm going to do is I'm going to look at each piece, and I'm going to do this one graphically, and then again, I'm going to do it numerically. So first off, this is going to continue on in this direction, okay? However, there's not a solid point here, so it's going to continue on in that direction forever, and then we have an empty hole, so this would be neither. This piece here, again, it's going to continue on that way forever. This piece is defined as I approach from the right. So this would be right continuous. So since it says for which intervals, it would be right continuous from 1 to infinity, and it would be neither from negative infinity to 1. Now, let's do this using actual arithmetic and algebra. Alright, so here's how I like to do these problems. First off, I like to create a number line, and I like to put these conditions on the number line. So we're going to be looking at 1 and 2. Now, if my value is less than 1, I'm going to be looking at x squared plus 3. If it's between 1 and 2, I'm going to be looking at 10 minus x. And if it's from 2 onward, I'm going to be looking at 6x minus x squared. Now, if I'm looking at any numbers less than 1, okay, then what I'm going to have, let's say I actually plug 1 into here, I would have the point 4. So as I approach from this side, okay, I'm going to have an open circle, and it's going to be approaching 4. Now, as I approach from the right-hand side, so values greater than 1, okay, I'll be using this equation. Then what's going to happen is I'm going to be approaching 9. Now, is 4 equal to 9? Nope, so we're not going to have any continuity here. Now, as I approach 2 from this left-hand side, remember, x value is less than or equal to 2, I'm going to be using this equation again. it's going to be approaching 8. Now as I approach 2 from the right-hand side, so values a little bit bigger than 2, I'll be using this equation. So 6 times 2 is 12, minus 2 squared, which is 4, so that's going to give me an open circle, and that value is also going to equal 8. Now since those equal, what that means is that these 2 points are going to overlap. Okay, so we're going to have an open circle coming from the right-hand side, but that circle is going to get filled in as we approach from the left-hand side. So what that means is that we are going to have, on this interval here, right continuity. And then this one is going to be played old continuous, so since they connect, this whole thing is going to be right continuous. And then this one, since I don't have a filled in circle on either side, it will be neither. Whoops. Neither is spelled N-I, isn't it? I before E, except like neighbor. Okay. Alright, so let's look at this next example. So what's happening here is that I have a piecewise function that's split at 5. Now I have x squared minus c, so that'll look something like this with an open circle because its value is strictly less than 5. And then I'm going to have 4x plus 2c, which is going to be a straight line with a closed circle, since x can equal 5, like this. Now, what this minus c and plus 2c are going to do is they are going to move these functions up and down, but at different rates. So what we really want to do is want to find a c value that's going to make these line up. So here's what we're going to do, is that we want x squared minus c to be equal to 4x plus 2c. But remember, we don't need them to be equal everywhere, and they're not going to be equal everywhere. We just want them to be equal when x equals 5. So we're going to plug in 5 squared minus c times 4 times 5 plus 2c. Now that's going to get us 25 minus c equals 20 plus 2c. And when we solve this, we're going to get c has to equal 5/3. Now, let's confirm that this actually makes our function continuous. So, to start off, anytime I have an x squared minus c, that's going to be a continuous function because it's a polynomial. Same thing for 4x plus 2c. So the only place I'm really concerned about is here. So if I take the limit as x approaches 5 from the left, which I would use x squared minus 5/3. Okay? Then what I'm going to get is I'm going to get the value 23 1/3. Now, if I take the limit as x approaches 5 from the right, I'm going to have 4x plus 2 times 5/3, which will also give me 23 1/3. So what this means is this tells me that the limit, since both sides are equal, as I approach 5 of my function f of x does exist, and it also equals 23 1/3. Notice as well that if I plug 5 into my function, I'll be using this bottom equation, and that will equal 23 1/3 as well. Which means overall that I have satisfied the conditions for continuity. My limit exists, my function is defined there, and more importantly, these two guys are equal to each other. Now I just alluded to it, but it's important for you guys to know. You get the following functions are continuous for free for every number in their domain. So if you have a polynomial, okay, that's going to be continuous for all real numbers. So this symbol means for all, so for all real numbers. Rational functions, remember, this says that it's going to be continuous for every number in their domain. Okay? So an example for this one would be something like x divided by x minus 4 is going to be continuous everywhere. But what's the one number I'm not allowed to plug into this guy? It's going to be continuous except at that very special spot where x equals 4. Okay? Root functions are also going to be continuous for every number in their domain. So remember, you can only take the square root of positive numbers. So as long as the stuff underneath here is greater than or equal to 0, you're good. Trig functions, inverse trig functions, exponentials, and log functions. So what I'm going to do is on our website on Canvas, I'm going to post just a little review sheet reminding you about how to find the domain for these specific functions. Specifically, rational functions, root functions, trig functions, and log functions. Okay, so be sure to check that out on Canvas. The other thing is anytime you add, subtract, or multiply two continuous functions, you're also going to produce a continuous function. Now the reason this is so useful for us when we're looking at limits is because we use limits to define a continuous function. Now that works both ways. Okay, if a function is continuous, what that means is that you can just take that number and plug it in and you don't have to show any of your work. So for example, here we have sine, which is a continuous trig function, the square root of x, which remember is only continuous for x values greater than 0, which 9 is greater than 0, so we're good. E to the x, an exponential function, also continuous. 4x, a polynomial function. So, if we put a continuous function inside another continuous function, multiply by a continuous function, and then subtract a continuous function, what that means is that we get an overall continuous function. So, we can just plug it in. So that's going to be sine of the square root of 9 times e to the 9th minus 4 times 9. That would be our limit value. Let's just clean that up just a little bit. Sine of 3 e to the 9th minus 36. Cool, so as long as you don't run into violating anything, such as dividing by 0, taking the square root of a negative, you can basically always just take a limit and plug it in and see what happens. Now, the next question I have for you guys is why is the statement that the limit of the square root of x equals 0 as x approaches 0 incorrect? Okay, so remember, for this to be true, our function has to be continuous. What does it mean for a function to be continuous? Well, if we take the limit as x approaches 0 from the left of the square root of x, that's going to not exist. Here's the reason. As we approach 0 from the left, that means that we'd be taking the square root of negative answers, and we're not working in the imaginary domain. If we take the limit from the right, however, it would equal 0. But again, because the left and the right don't equal, that means that the overall limit as x approaches 0, the square root of x, does not exist. So how can we rewrite the statement so that it's correct? Well, we can rewrite it by adding that little positive to the top. So just keep an eye out for this. Sometimes it's a favorite question on homework or maybe exams. All right, the last theorem that we're going to discuss in this section is called the intermediate value theorem. So here's what the intermediate value theorem states, is that if a function f of x is continuous on an interval from a to b, and remember those are hard brackets, so that means that we're taking a and b and we're including them so we can actually plug them into our function, and there's some number n between f of a and f of b, then there exists some c value between a and b such that f of c equals n. Oh, what? So here's what I do. I've been doing math for a really long time, and I've read a lot of theorems like this where I get to the end and I'm like, I have no idea what you just said. So let's slow down and draw a picture. So we have a function that's continuous. Cool, that means I can draw it from point A to point B and I don't have to lift up my pencil. It also says that I have an interval from A to B. And those are close, that means that if I actually plug them into my function, I should get some value out. So here I have f of a, okay, that would be this point here, here, okay, I would have f of b. All right, so f is continuous on an interval from a to b, got it, drew it out, and n is some number between f of a and f of b. So n. Oh, I almost forgot. F is a continuous function. That means I can draw it without picking up my pencil between a and b. Now here's the important part. It says if it's continuous on an interval and there's a number n, then what I should be able to do is that I should be able to work backwards, track it onto my function, and there should be some c value such that when I plug that c value into my function, I'll get n out. Alright, so here's why this is so cool. There's a lot of things in our life that are continuous, okay? And sometimes we don't even care what the actual answer is. We just want to know that the answer exists. So let's say that when you were born, you were like 22 inches long, okay? So a little bit under 2 feet long. And then as an adult, let's say that you made it to at least being 4.5 feet tall, okay? So because as you grow continuously, that means that you don't just sprout up randomly in the middle of the night. There was some point in your life where your height was exactly 3.141592 feet tall. That means for even just a split second in your life, you were exactly pi tall. Okay? So, remember though, you have to think of f of x as a continuous function or it doesn't work. So something that's not continuous would be like my bank account. So for example, let's say that every 2 weeks I get paid $500. Okay, I don't. That would be really sad as a math professor that I only get paid $500, but just go with it. Okay, so if my bank account only has $12 in it and then I get paid, it jumps from $12 to $512. Okay, so does that mean that at some point in time my bank statement had exactly $400 in it? Well, no, because it jumped. It's not a continuous addition. It's not like they sit there and put 1 penny at a time into my bank account. Let's show that the function f of x equals e to the x takes on the value pi somewhere on the interval between 0 and 2. So first off, I'm going to draw a picture of the function e to the x. So what e to the x looks like is it looks something like this, okay? And at 0, I'm going to have 0, e to the 0, which is 1. And then at 2, so this was at 0, at 2, I'm going to have the point 2, comma, e to the second, which is just a little bit above 4, okay? So what I want to do is I want to show that this function takes on the value of pi somewhere between 0 and 2. So if I look at this, pi, remember, is 3.141592 blah, 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 blah. Okay? I want to show that there is some point where I could plug that value c in and I'll get pi out. Alright, so first, remember, you guys always have to do this on an exam or anything. First, note e to the x is continuous. You don't have to tell me why. Okay, we get it for free. But you do have to acknowledge that it is continuous. Now, the second thing we want to do is we want to plug in these endpoints. So e to the 0 equals 1. E to the second is around 7.38. My bad, let me change that on here. So not 4, it's actually closer to 7.38. All right, so here's what this tells us, is that since pi is somewhere between e to the 0 and e to the second, there is a c such that e to the c equals pi, because our function is continuous. Okay. Now, for this one, prove that there exists a solution to the equation natural log of x equals x minus the square root of x on the interval from 2 to 3. Now, here's my first hint to you. Okay, is take everything and move it over to one side. So we're going to have 0 equals x minus the square root of x minus the natural log of x. Okay? Now, what we want to show is that f of x, so this function here, equals 0 somewhere between 0 and, between 2 and 3. Now, here's something you have to note, and again, just like we did up top, this is a continuous function, the square root's a continuous function, the natural log is a continuous function. Note that all three of these are continuous between 2 and 3. So, if you subtract 3 continuous functions, then you have f of x is continuous. Have to note that. Have to. Now, if 2 or 3 were either negative numbers, we couldn't use this because the natural log and the square root aren't defined for negatives. So the second step is we're actually going to take these endpoints and plug them into our function. So f of 2 would be 2 minus the square root of 2 minus the natural log of 2. Okay, f of 3 would be 3 minus the square root of 3 minus the natural log of 3. Okay, and let's see what those are. So I'm going to plug them in real quick. All right, so when I plug 2 into my function, what I get is that I get out a negative 1.0, or negative 0.107, and when I plug 3 in, I get positive 0.169. So, since 0 is between that positive and that negative number, then there has to be a solution to this function. Okay? So there's a c such that f of c equals 0. Now, before we move on, just like before, I think it's kind of helpful to draw a picture. So here's what this is telling me. Is that if I plug 2 into my function, okay, my y value is going to be negative 0.109. So it'll be somewhere down here. Okay? If I plug 3 into my function, I'm going to get 0.169, so somewhere above. Now, since my function is made up of continuous functions, I can't draw a line from 2 to 3, okay, without crossing here at this point, some point c, where my y value equals 0, which is what I wanted. I wanted to find some c value where it equaled 0. Okay? All right, very last thing is, can we use the intermediate value theorem to prove that there's a solution to 1 over x equals 0 on the interval between negative 1 and 1? So, if I plug negative 1 into this, so we're going to let f of x equal 1 over x. If I plug in negative 1, I'm going to get negative 1. And if I plug in positive 1, I'm going to get positive 1. And 0 is in between those guys. However, whoops, my apologies, that should be a positive 1. However, if you try to solve this as hard as you might, you're not going to get a solution. Why not? Well, here's why not. Is if you actually graph the function 1 over x, what you're going to see is that you don't have a continuous function. Okay? So it actually fails to be continuous between negative 1 and 1 because it has this vertical asymptote. So you can't get from this point to this point in a continuous line. Okay? You have to have a little jump. So you have to go down to negative infinity and then jump back up and go to positive infinity. So the reason we failed in this case and we can't use the intermediate value theorem is because 1 over x is not continuous on that interval between negative 1 and 1.